Good? Everyone hear me? This is cozy, isn't it? Thanks for all turning up, coming down to the cellar, 10:20 in the morning. I am going to talk to you about Addresscloud and the work that we do there, but also about the story that I've been on. So to set the scene, my name is Tomas Holderness. I'm CTO at Addresscloud. We provide property and risk information to insurers around the world. To do that, we deal with a lot of geographic data. My background's actually in geography, and spoiler alert, we like using serverless. But one of the things that we have to think about and have to do is work out how we get our geographic data into a data model, into a mode that allows us to use it with all the good stuff that we get from serverless in AWS. And we've developed over the years some patterns to do that, which I thought I'd share with you today. Because we've not really seen anyone else talking about this. We've seen lots of geographers talking about data science, and I'm going to touch on that in a bit. But actually, how do I model my data so that I can use serverless-first technologies and data stores in AWS? Not talked about so much. So, clicker malfunction. Let's use laptop malfunction. Great, we're there. So as I said, my background's in geography. I went to university and studied geographic information science. I've always been really interested in geography, and in particular, interested in maps. I've always enjoyed maps, making maps. A lot of people out there like maps. They're a really kind of like evocative thing. You get beautiful old maps. People are normally quite interested. And I discovered this topic, this area, geographic information science, that combined my love of geography and tech. I've always been interested in tech as well. Saved up as a kid on my paper round for years and years, and then bought myself a Pentium desktop, and I was away poking around, messing with different bits of code and bits of software. And I was like, okay, what is this thing, GIS? GIS is all about getting the computer to make a map for you. And really, I found my jam, my niche. That I was like, this is awesome, and the people that work in that industry are also really awesome. And so I studied that, and I was like, this is brilliant. I'm really enjoying it. It brings these two things together. And I've kind of forged a career at working at that intersection of interesting geographic problems, but using technology. We just heard in the keynote about the kind of wave theory of like the next wave is coming. It's probably going to be AI, ML. So now I'm kind of already looking, well, we've got this geographic data. What interesting things can we do with that data, with geography, and with AI and ML? But we're not going to talk about that too much today. So I stayed on at university, and I did a PhD because some colleagues said to me, come, we'll keep you love it here, you love this topic, come and work with us. And so because my background is in academia, I've got a few slides to share with you to impart some knowledge, because I couldn't stand here and give a presentation without hoping for you to learn something. And the first thing that I wanted to share is this concept that geographers talk about stuff being more related when it's close together, and stuff that's further away is less related. And it's pretty obvious, right? Vegetation, trees, whatever it might be, in England have more in common with each other than in a Mediterranean climate. Or types of food. Curries from Vietnam are more like each other than curries from India, for example, because we know that humans and physical forces are all kind of interrelated, but they're more likely to be related to each other if they're nearby. And that's a key principle of geography and of geospatial data science, measuring how far things are and how related they are to each other. Another kind of key thing that I wanted to sort of impart on you today, and that we talk a lot about in GIS, is the concept of topological spatial relationships. So that's saying we can talk about the relationships between two or more entities in discrete space, and we can use set theory to describe that. So we can say, is the house in the land parcel? Are the two houses next to each other? Are the two houses actually adjacent and touching, i.e. they're a terrace, or are they spatially separate? Are they distinct? Are they two detached houses? And what that means is we've got a really nice way. Eggenhofer kind of came up with this idea a long time ago now, and it's been developed and taken forward over the years. But we've got a really nice way of using maths to represent how stuff is spatially related. Super simple. And what that lends itself to is a relational model, right? Because we're saying, is the person in the house? Are they in the garden? Are they on the street? Where is the car? Does the road cross the railway at that point? If so, is it a bridge? And so I start to think in 3 dimensions. And we can encode all of those relations using that spatial relational model, and we can use a relational database to store those relations, and then we can ask really interesting geographic questions of our geographic data, like, do those two features intersect, or are they far apart? And that has been the kind of de facto standard in the industry for many years now. We have some kind of spatial database in the back end for our application. We have some kind of web server, middleware, right, that talks to that database, and we have an API. And then we have some front-end application. I'm sure some of you used Google Maps to get here today, right? How do I get to Victoria Warehouse? Which tram do I take? Those are all questions that are coming ultimately from a big GIS using Google Maps or Apple Maps, where you're asking some geographic question, it's hitting a database, coming out with the answer, and then rendering it on your client. Ultimately, those are the kind of tools, excuse me, that we're interested in building. So, but I didn't just stay and build GIS tools in academia, kind of take off the shelf, just doing the GIS, just doing the technology. I actually got quite involved in a particular set of applications in the world. Climate change is literally the hot topic. It's here, and we know it's changing. Our climate is changing. We know it's causing more extreme weather events. And this has been around for a while. This graph from the IPCC, where we fundamentally know that we're going to, not only is the average moving, but the frequency and the severity of those extreme events is also increasing. And I've worked with spatial data sets on temperature, but I've also worked with spatial data sets on flooding, because this is a topic that is impacting people around the world. As the atmosphere heats up, we've got more moisture, and then we have more flood events. I'm going to come back to insurance, I promise you, at some point. You can hopefully see where I'm going. So flooding is a really big problem around the world. And a colleague said to me, I was working in Australia at the time, a colleague said to me, Jakarta in Indonesia, 27 million people in one city, has serious flood problems every year during the monsoon. Is there anything that you geo folks can do to help us? And I was like, well, yeah, let's make a map. Okay, well, where are we going to get the data from? There's no official data about where the flooding is. But everyone's on social media, right? And Jakarta, Indonesia, in general, has a very, very high concentration of people on social media. So we started to build relationships with different social media organizations. We can see an example here from a local app called Clue. Flew to San Francisco and met with Twitter and got them on board, and we started to build this real-time application where people could have a conversation with a chatbot, and they could report. They could say, yes, my street, my house is flooded. And we could take that information and plot it real-time on this map. We start to see really interesting examples of infrastructure failure, people like reporting before any kind of sensors or other device is going to tell you that this thing has happened, but like this levee has collapsed, this is a major problem. And that's incredibly valuable information. It's valuable to see it on a map for other people so that you can plan your route to work and avoid this. It's invaluable to the government so that you can do disaster planning and response. And it's valuable to scientists because we can start to see how our infrastructure is responding to climate change. And we took that map and then we put a version of that map into the emergency control room as well. So now for the first time, the city and the mayor have got this real-time bird's eye view of what's going on the ground, and so they can start to coordinate response teams. And this was all predicated on what we showed before. I've got a spatial database which I'm populating with all of these tweets or these messages, and I've got a server that sits in front of that, and I'm making requests of that server for that database to say, in this neighborhood or in this area, like show me the flood impact. So exactly the same model, but incredibly high volume, incredibly peaky, right? So most of the year, 300 days of the year, there's no flooding. No one bothers about this map. No one uses it. Like everyone's doing something else. And then all of a sudden, you get the cloudburst event, you get the flood overnight, and everyone logs onto the map. And so we saw the load go up. Everyone's talking about it. So we've got thousands of tweets a minute coming in from Twitter. So we started to have to build scalable systems. And this is the challenge, right? Using that traditional database server technology, we were running it on Beanstalk with an RDS, standard stuff at the time. Really having to work quite hard to make sure that thing would scale really, really quickly to meet demand, but then also, because we were grant funded, make sure that it would scale down again so that we weren't paying for it afterwards. And of course, I mean, you'll get it. Immediately it was like, well, maybe we could use serverless to do this. Before we got to serverless, though, we started to sort of tweak around the edges and think about how we make this system more efficient. There's a really nice package by a guy called Mike Bostock, who creates the creator of Observable. Notebook, some of you may have used that for data science, creates this thing called TopoJSON, which is a way of compressing geographic data using topology. So back to the slide I showed at the beginning with Eggenhofer, now thinking about spatial relationships, but just using that as a data transfer mechanism to compress the data between the database, between the server, and between the application. But these the same principles that I started with at the beginning, but they're just being applied, in this case, in JavaScript. So this was the map at the end of the first monsoon season, right? People loved it because they were the first time they had this visibility. Everyone could see what was going on. These are all of the tweets and the messages that people had sent saying, yeah, there's a flood problem here. We managed to put it on a smartwatch, which was also pretty cool. And then we scaled this thing. We said, well, we've got this technology that works in Jakarta. Why can't it work in other cities? And so worked with some colleagues out of MIT in the States. We did a pilot in Florida during hurricane season, in India, and the guys in Jakarta are still running instances of this around Southeast Asia, where there are lots and lots of people living in lots of cities, and there's lots of problems with flooding because of the nature of that tropical climate. So, Tom, you're thinking, at the beginning you said that you work in property insurance, and that's what Addresscloud does. How do we go from being a kind of climate change researcher but building real-time operational systems to working in property insurance? Well, it's kind of similar, right? It's just geography, and it's just the same kind of set of perils, but this time it's not really people, it's buildings and it's houses. So when you go and get your property insurance, the things that the insurers are interested in is it in a high flood risk area? Do you live next to the river? Have you got a large tree in the garden that's going to cause you subsidence because you're on a clay soil? Is it a thatched roof that's got a high risk for fire? Do you live above a fish and chip shop? These are all geographical questions, right? These are all about adjacency, about how close other stuff is around to your property that feed into an insurer's model to give them a view of the risk of underwriting. So our mission at Addresscloud is to build a view of risk, a map effectively for every building on Earth so that we can answer this question at any time, anywhere, any place, to allow insurers to make better underwriting decisions. So here's an example of one of our applications. This has been running since 2019. This is a great wildfire model from our colleagues in the US. This is West Coast, California. And what we're seeing here, these zany colors, these reds, these pinks, these yellows are telling us the type or the propensity for there to be a wildfire event. And we've dropped a pin on that map which represents a particular address. So we've done some geocoding. We've said, here's an address. Get me to a point on the Earth's surface. And we know that that point is in a building. And we know the building has got, in this case, it's got what's called an interface high. So it's quite likely that that building, that property is going to be affected by wildfire. And we can look not just at the building, but we can look at the land parcel, and we can also look at the neighborhood so that we can kind of account for the different perils, move at different speeds, and have different propensities to spread. Wildfire's a really good one at spreading over large areas very quickly, as we saw in the LA fires this year. So how do we do that? How do we make this thing a reality? How do we render the map that I just showed you? Well, we have what we like to term the reverse Pac-Man diagram. So we gobble up lots of data from different suppliers. Some of them are commercial, some of them are open source. And our data team does a whole bunch of magic, I'm going to call it, but effectively data science, to get us down to a view for every property of all of those different perils. So we're going around the world saying, we know where all the buildings are, let's tag them with all of these different perils. And then we serve that information out, right? We serve it out through a suite of APIs. We serve it out through a suite of applications. So big insurers come to us and say, we've already got our workflow. I want to know about, for every property that I underwrite, I would like to know the flood score, please, and they can just plug it into our API. Mid-sized, smaller insurers come to us and say, I'd like to do that as well, but I haven't got the capabilities to do that. So can you give me an application? And we say, yeah, sure, here's a map so you can go and do that manually, or here's an interface to use a spreadsheet. And so we're really answering 4 questions, right? Given an address, we're saying, where is it in the world? What is it? Is it a flat? Is it a house? Is it a school? Is it offices? How risky is it? What bad stuff is likely to happen to it? And then also, we can also do what we call accumulation management, which is, and what other things has the insurer got on their books nearby that might cause them what we call an accumulation hotspot, where all of the risks independently are okay, but if you're writing every property in a terrace and the whole terrace has a flood, that could be a real problem for an insurer. They'd be overexposed and they'd have to go and get reinsurance. So that all sounds pretty good, right? I've talked about geography, talked about bringing together some data sets, talked about serving it out. The real challenge for us is are these 3 things. Doing that process at scale, so we're multi-region, we've got customers around the world. They're high volume. It's a really weird industry in that the requirement is to have to be able to ask for every building or any building anywhere on Earth for a flood score, for a crime score, for whatever it might be, at scale in real time, all the time. Because people are buying insurance all the time. So if we can't answer that question for an insurer, then they can't give a quote, and then they'll lose a piece of business. So when you go to somewhere like Compare the Market here in the UK, and the meerkat runs off and says, I'm off to go and check the Ordnance Survey, I'm off to go and check for flood data, all of that traffic is coming to us. So we're doing all of those lookups in real time and responding to all of those insurer requests. And the key thing for them is that we're doing it at scale, it's at volume, it's global, but also consistency. So it needs to be quick. It doesn't need to be the fastest thing ever. It's not like high-frequency trading, but it needs to be consistently good. We need to be able to say, hand on heart, yeah, you'll be able to plug into this. It's an all-you-can-eat kind of model, consume as many flood scores as you want over the year. And we'll consistently, P99, get back to you within a half-second latency for every property. These are some of the customers that we work with. Some of them you will know, they're household names. Some of them you won't know because they're commercial insurers in the market space. But just to give you an idea of kind of who we power here in the UK and then also globally. So how do we do this? I'm the CTO, I'm responsible for trying to get the team together with the technology to say, okay, this is how we're going to answer these questions at scale with volume consistently. So we made some bets, and this has been a journey in the last couple of years that we've been on. The first bet was serverless. It's pretty obvious. We're going to start to work down our stack and use the serverless technologies that AWS offers us to wean ourselves away from that beanstalk application model to start to use API gateway at the front end, lambdas for our logic, and then something for our data. But that's the real trick, right? How do we do our data? Because the others are kind of obvious, out-the-box solutions, but what do we do with all this geographic data? So we started with Aurora Serverless, which is great because it supports Postgres, and Postgres has an extension called PostGIS that allows you to represent spatial types. And the kind of magic stars in this icon do a lot of heavy lifting here, right? Because we had Serverless v1, and then that was deprecated, and we've gone to Serverless v2, but it's not really serverless. It's actually kind of a pain to manage. And the spatial database there quickly kind of became a bottleneck. We still really weren't getting a full kind of serverless experience. We're still kind of having to think about where the instances are, how many we've got, what are the scaling points in response to all of that traffic that's hitting our service. So we're a fan of memes in the business. This one goes around a lot. We're going to need a bigger database because we just couldn't work out as we scale, as we want to get a view for every building in the world. Okay, how are we going to put that? We can't put that in a single database, particularly where a database like that where my storage and my compute are coupled together, right? And that's kind of the thing that Amazon have been working on with Aurora, is decoupling those things behind the scenes, but giving you that Postgres, PostGIS compatible layer. So we've started to look at technologies that are emerging from the industry, and this is kind of led by a whole bunch of different people working in different problem spaces, but are all coming together of, I've got geospatial data, how do I make them cloud native? What formats do we need for the future going forwards? And I'm going to talk to you about a few of them today that lend themselves really nicely to being used in a serverless way. So the first one is when I want to render some tiles on the map. So when you look at the map to get here, Victoria Warehouse today on Google Maps or Apple Maps, it's not one image that you're seeing. It's lots of small images that come down the pipe for the area that you're looking at on the screen. And as you pan and zoom and move around the map, we're getting different tiles coming down the pipe. And that's an efficient way of chunking up the Earth's surface so that I don't have to give you a map of everywhere in the world on your device. You can just request the tiles that you're after at that time. And this is a really obvious one, right? But not a lot of people do this. We still see that there's a lot of people running quite traditional container-based solutions for serving out map tiles. Whereas actually, I've already partitioned up the world into all of these little tiles and these little squares. I can put them in a bucket, I can put API gateway in front, and then my client can make requests. So super simple pattern, one that we're a fan of. We do this at scale. It doesn't really cost us anything, but it means that we've got 2,000 users that are rendering all of those little map tiles for anywhere in the world at any time with 30 different peril layers that they can also load on top, and it works really, really well and efficiently. The next one is, okay, that's great if I've got a map, like a base map, but what about where I've got like a flood model that's incredibly high density data? This is an example for the UK. It's 200 gigabytes at a 5-meter grid, so we're counting or measuring how much water is in each 5-meter grid for the whole country. We could do this for North America. It's even bigger. Spain, France, Italy, and so on. So we've got what we call, these are in a kind of bitmap format. For those of you that work or are exposed to GIS, you might have heard them called rasters. So it's a big old pixel image. So how do we get that handful of pixels around the property that we're interested in? Because I really don't want to, again, send this whole 200 gigabytes to the client. I want to be able to spatially index that and say, I'm just interested about the flood scores around me. There's a format that emerged about 5 years ago now called a cloud-optimized GeoTIFF, which is a way of organizing the information within inside a GeoTIFF so that it's pre-indexed, it's quad tree indexed ahead of time. So, and that quad tree index is spatially linked. So I can say, I'm interested at this point in the Earth's surface, just get me the part of that file that represents those pixels on the Earth's surface. So that's a super neat idea. It's, again, a really simple pattern that we've worked with, where we pop that big raster file in a bucket. We put some logic in front of it. There's a few different libraries that do this, but there was one called Rasterio from out the US, where we can say, I've got my latitude and longitude, so my XY coordinate of the building or the property of interest or the caravan park or the school. Convert that into pixel coordinates, so convert that real-world geometry into what are the pixels I need from this image. It does it almost immediately, and then we can use those pixel identifiers to make range requests against our object in the bucket, so we only get back that handful of pixels that we need. And this is something that we do at scale in real time, and it works really, really well. OK, now we're on to just see how we're doing for time. Good, we're on time. I'm going to let you go on time. You're not going to be in here all day. But this is kind of the last kind of pattern that I want to talk to you about, and is really one that I think is really pushing the boundaries, and hold our hands up and say, we didn't invent this. All we've done is take something that's kind of emerged recently and seen that there's an opportunity to use it for spatial architectures. And the thing is, the topic that we're talking about is discrete global grid systems. So again, it's a way of partitioning up the Earth into different shapes ahead of time, so that I don't have to do spatial queries in my database. I've already chunked the Earth into a series of small bits. There's lots of different ways of doing this, different shapes and different patterns, and they have their own advantages and disadvantages. The one that we use is based on hexagons and comes from Uber out of the US, and it's called H3. And this is just a way of bucketing stuff in the Earth's surface. So I've got geography. I'm interested in the distribution of floods or the distribution of wildfires all over the Earth's surface. We've got all of that data. OK, well, we can cut the Earth into lots and lots of small hexagons ahead of time. We know how all the hexagons relate to each other, and we also know we can zoom in and out. So each hexagon has child hexagons, and each hexagon also has a parent hexagon. And so that's a really handy spatial system where ahead of time, outside of the database, we can say, here's a spatial representation of the Earth. And we do that. So there are others. Google has one called S2. There are lots of different ones out there, and they all have their own advantages and disadvantages. But H3, in my opinion, is pretty cool. Each hexagon cell has its own internal coordinate reference system. One of the really nice things that Uber do is they use it to do the directionality of the cars. So when you're ordering your Uber car, the app can work out in real time which cell the car is coming from, and then that's how they kind of start to do an estimate of how long your drive's going to be. And then they get into the actual routing, but it's all predicated on it's 3 cells away. And they needed something that worked globally for them, that was consistent anywhere in the world. So we take an address, and this is what Addresscloud does. We take an address like Victoria Warehouse here in Manchester, and we flip that address in real time to a cell index using the H3 library. So then we've already got a key value system, right, where we've got a cell index for whichever cell fits the whole warehouse in. And then I've already pre-tagged my flood information because the canal is just behind me, behind this wall here. So there'll be a reasonable flood score, I imagine. And I've already pre-tagged that. So get the cell index. I've got the flood score for that cell ahead of time. Makes it really, really easy, quick key value lookup. So then we can develop a really, again, super simple pattern, but not something that I see lots of people talking about, where we can use any key value store, in this case Dynamo, against my H3 cells for the areas that I'm interested in, and I can make GET requests. And I can do that all day, in and out. It's serverless mode. I don't have to monitor it even. Like, it's just gobble up DynamoDB capacity, keep going, and it will scale up and it will scale down. Absolutely fantastic. And the H3 library, again, standing on the shoulders of really smart people who wrote a very, very efficient library to be able to go from real-world geography to a hexagon and back again in milliseconds. Skip that slide. In the interest of time, last few things. Look into the future. some really interesting developments coming out in the data lake, data science space that we haven't really talked about, but this will be the foundation of how we move our geographic data into our Gen AI models, because both Iceberg and Parquet, which are both columnar storage formats, are getting native geography support. So it will just be built in. So I'll be able to say, hey, give me an Iceberg file that represents all of these curry houses, or give me an Iceberg file that represents my flood scores, whatever it may be, and I can store that in my data lake and then ask interesting geographic questions. But because they're cloud native, I don't need to do that in a database, right? I can do it at the data lake level. And so I'm really excited to see both how these help in the first instance our data science team, because I think obviously they will, but then how can we pull that forward into our serverless world? Can we use these stores? Can we pop them in S3 and start to query this data just like we do with the others? Will it be performant enough? How will that work? There's a lot of scope there, but there's a propensity to be able to build almost virtually scale-free services on top of those data formats that allow us to query data without even needing a database. Okay, I'm going to leave it there. You've all been excellent. Thank you very much.
That was great. Thank you, Thomas. So have we got any questions? We've got time for a couple of quick questions.
Hey, when you're serving your responses from your S3 to your API gateway, how are you dealing with the tile size? So we're using, do you send all the data through either a REST or a HTTP, or do you use signed S3s to get around the max response size?
So the way that we do it for rendering tiles on the map, the tiles are what called vector tiles, and they use the protocol buffer format, which is or subset of protocol buffer format that was developed by Google and Mapbox. It's just a really it's not a problem in terms of they're minuscule. They're like, each tile is like kilobytes because it's super compressed, so it's never a problem. But you're right, we have hit that way with like, okay, how do we basically, it's quite a thin pipe sometimes through API gateway, it feels like it. It's just a case of making sure that those tiles are as efficient as possible, or splitting them. So every tile, you might have a tile that has, if you have a tile that has all the houses and the building and the flood and the fire, it's probably too much. So we'd split those into separate layers, effectively, separate tiles. So you maybe make 4 requests for 4 different tiles if you're interested in 4 perils.
Okay, thank you.
I totally forgot as well. Team are going to be annoyed to put this advert on the slides. If anyone's interested, no recruiters. If anyone's interested, we're looking for data science people and an engineering director at the moment. So drop me an email.
Any takers or more questions?
One at the back. There's one here.
Sorry, I was really late to your talk, and I'm quite old school as well. In the past, I've used geohashes to do something that looks similar to H3. Can you just a quick contrast as to why H3 is better than geohash, maybe? Geohashing versus H3.
Yeah, I mean, it's like pick your weapon, right? They do the same thing in different ways. Geohashes, I think, are square. So the Earth is kind of rugby ball shaped. So the shape of the squares or the size of the squares changes depending on where you are. Anyone that studied, looks at the old Mercator maps, you can see this, Western Europe's massive, and it's actually a lot smaller. I think geohashes have that. We just picked H3 because it's got that nice, nested geometry thing going on for it. But the children don't quite fit in all of their parents, so there are edge cases to it. It's not perfect. You could do it with either, effectively, just in the knowledge of what are the limitations of the grid system I'm using. Yeah.
Thanks. So I actually work in precision agriculture, and we also use global grids to do these kind of analyses. At the risk of repeating the previous question, I'm curious about why you landed on H3 over S2. We decided on S2 simply because those overlaps made me feel a bit icky. And the library was slightly easier to use. Was there anything deeper as you've done the doctorate in this that kind of changed your choices?
I'd love to say that there was, and I've got some really smart answer, but no, there wasn't. It was just we kind of, technologists, right, this is cool and it kind of works, and then we just kind of roll with it, and here we are. So I'm not good at, yeah. I think, as I said before, choose your weapon. I think that's why I didn't say spatially discrete grid systems is the terminology, right? Because there's different ones, they've all got their own pluses and cons. I really like the H3 system, but it has got edge cases. I'm not selling it, and yeah.
Right, any more?
I think there's one at on this side, on my right.
Hiya. If you've got a property that is on like the edge of a H3 region, do you pick a different like resolution, or do you pick the tiles around it?
Cracking question, because it's a real problem. Yeah, so when we're assigning a score, what we try to do is not just look inside one cell, but it's to look at the adjacent cells. And to the previous question, one of the things that H3 does really well, but I don't know if S2 does this actually, but it has adjacency in it, like in the indexing system, so you can really quickly get me all of my adjacent cells with, like in the K-ring, like that. It's incredible how they kind of did that crazy binary structure that I don't really understand, but it works really, really well. So yeah, we'll say we won't just look at that cell, we'll make sure that we account for neighboring cells, and then if one of them's got a really high flood score, we're like, oh, like what's going on there? Like, and then we'll run a little subroutine to make sure that we're picking up the right things. And we had an issue this year actually where even like 10, 15 meters can make a massive difference. And so it's really important for us to make sure that we look outside of our like immediate hexagon or postcode or whatever it is, but to account for adjacency.
So if the property is like in the middle of a hexagon, but the hexagon next to it has a really high flood score,
yeah,
would you then like look at the distance between your property and that hexagon?
Yeah, at that point we might actually drill down to the raw, like the spatial data, and be like, okay, how far away is this thing, and what is the severity of the flood? And we might take a pessimistic view and say, okay, we're going to tag that property with that flood score, because remember the flood score is a model, right? It's an imperfect representation of the world and what will happen if you pour a jug of water in and where that water will go. And it's at 5 meter resolution, which is an incredible level of precision, but it's not necessarily like 5 meter accuracy. So the data providers will always say, don't just take one pixel, like take basically, they draw a circle, we use a hexagon, and you can vary the size of that thing. One of the things that we do quite effectively is for commercial insurers, which we've got quite a few of, we would say, we won't just look at where the mail gets delivered, but we'll look at the entire site and all of the buildings on a site. And again, that's with hexagons, and that works quite well. So we can say, what's the worst flood score on this site as opposed to just here at the front door.
All right, that's great. Thank you very much, Thomas. That
Thank
was
you.
Brilliant. Anybody back in here? We're back in here at 11:20.